Right, good. Is Lewis structures. Now Lewis structures are pretty much an achieve level question or a merit level question. It's following on from what you did at level 2, so it's just extending on to compounds that are cations or anions or don't have an octet for various reasons, and we'll go over that. Then we'll look at electron geometry, which is the areas of negative charge or electron density around that central atom, and from that you can work out the shapes of molecules. So that explanation is what gives the merit and excellence, and from that you go into polarity. So you need to first of all know how to do Lewis structures before you can do shapes, before you can do polarity. They're all linked up. Okay, so Lewis structures, just going over, refreshing what you did at level 2. So please yell out if you've forgotten or if I'm going a bit too fast. But really what we do with Lewis structures is we arrange the valence electrons around all the atoms in the molecule or ion so that each have got a stable octet. So the first thing you do is you count the number of valence electrons. So this is going to be a bit of a trick question because at level 3 you meet xenon. What group is xenon in? I'm just wondering, you must probably don't know all these things off by heart. Does everybody have a periodic table handy? There's one in every single booklet or at the back of a course and assessment guide. Yep. So what group? Okay, well, let me say it this way. Xenon is one of the noble gases. So it's in the last group, group 18. Does it have valence electrons? Yes, it's got 8. So remember, the number of valence electrons always corresponds to the last digit of the group. So anything in group 1 has got 1 valence electron. Anything in group 2 has 2 valence electrons. We'll forget about the transition metals. If you carry on with university, you will deal with those. But we just go on to the P block. And so if you've got group 13, then it's 3 valence electrons. Group 14, like carbon, is 4 valence electrons. Group 15, like nitrogen, phosphorus, 5 valence electrons, and so on, until you go all the way to group 18, which is 8 valence electrons. That's important because you need to count up all the valence electrons for every atom. So if we have this particular molecule, it's formaldehyde, H2CO, and you're asked to draw the Lewis structure. You probably came across this at level 2 as well, but it's what we're saying is I've got 2 hydrogens, each hydrogen's group 1, so it's 1 valence electron, carbon group 14, so it's 4 valence electrons, oxygen group 16, so 6 valence electrons. So you can see 2 times 1 plus 4 plus 6, so we've got 12 electrons to arrange. So your next step is to say, all right, of those 4 atoms, or 3 different types of elements, which one is the central element? Which one is the one that the others are going to bond to? Now you'll come across some at this level where you might not just have one central and all the others around it. An acid is a common one. The hydrogen in an acid is not bonded directly to the central atom, but you've just got to decide which one of those. So there are 2 things you think about when you try and work out which one it is. It's the one with the highest valency normally. So remember I spoke about using the periodic table to get the valence electrons. Now the valency goes up and then it goes down. So group 1 is 1. Actually, it's not the highest valency, Rebecca, because you're thinking of the number of valence electrons. It's a common thing to get muddled up with. Valency is the combining power. Valence electrons is the number of electrons in the outermost shell. Okay, so oxygen, you're right, has got the most number of valence electrons. But valency is the combining power. So by that we go, okay, anything in group 1 has got 1 electron to share or give away. So it's got a combining power of 1. Anything in group 2 has got a combining power of 2 because it's got 2 electrons to share or give away. Group 13, as I say, we miss out the transition metals because they do their own, it's a little bit more tricky. Group 13 has got 3 valence electrons. So 3 valence electrons, you could still give 3 away. It'll be quite difficult because you've got to remove something negative from something that's already positively charged, but you could. So you could remove 3 electrons, or it could share. By the time you get to group 14, it doesn't like giving any of its electrons away to form a cation, but it could share. So carbon comes in here and silicon. So it's got a combining power of 4. It can share its 4 electrons. By the time you get to group 15, it's got 5 valence electrons. Its combining power is actually now 3. It's dropped down. The reason being is, if you think of the periodic trends, it's got a lot more nuclear charge of what we did last week. So it's not going to share as easily all 5 electrons. It would rather try and gain 3 electrons. So nitrogen and phosphorus, they have a valency of 3 because they'll combine with 3 of the electrons and share 3 of the electrons to get 3 others to them. Oxygen is going to combine and share only 2 of its electrons. So it's got a combining power of 2. Chlorine is a combining power of 1 because it'll only accept 1 electron, or perhaps share 1 electron. And of course the noble gases don't share anything. They have actually a valency of 0 because they don't combine. Although you'll see we'll have examples of xenon. You can make xenon actually do something under high enough pressure. So once that's clear, is that everything clear between valency and valence electrons? You can say yes or no, and don't worry if it's if you say no, because then I can just make sure that I give more information perhaps after the lesson. Okay, so carbon is that one in the middle, group 14, so it's got a valency of 4. Hydrogen's valency of 1, oxygen's a valency of 2. So carbon is probably the central element. The other way you can work it out is the one that's there present in the least amount. Now we've got 2 hydrogens, we've got 1 carbon and 1 oxygen. So that's not that helpful, that little, it's not really a rule, but it's a sort of a guideline. So the way we decide is carbon, highest valency, so that's in the middle. There are 2 elements that are never in the middle, and that's hydrogen, because it'll only ever bond once, although again at university you'll find some exceptions, and the other one is fluorine. Don't ever make fluorine bond with more than 1. Fluorine is, remember, that very highly electronegative, in that top right corner, it hates sharing. It will not share any electrons apart from 1. So that's why fluorine can never form 2 bonds, it can only form 1 bond. Right, so we've decided on the central atom, and now what we do is we take those 12 electrons and we start arranging them. So we've got to put the other electrons in, other atoms, hydrogen and oxygen, and we put in the pairs of electrons. So we've used up 6 of the 12, and now we start placing the rest around the outside, like that. So I had some left over. Do I have any electrons remaining, or have I used up all 12 electrons? Just say yes or no. So yes, I have used up all 12, or no, I haven't. Okay, yes, I have. Great, Sophie. So it's 2, 4, 6, 8, 10, 12. So I don't have any remaining electrons. I can skip step 5. Now this next step is I've got to check for an octet. Anything that's in the second row of the periodic table has to have an octet because it's got no 3D, it's got no third energy level, so it's got no 3D electrons to make it out of its octet. The only exceptions would be beryllium and boron. They can get away with no octet. In other words, they'll just have 6 electrons around them or 4 electrons around them. And hydrogen obviously never has an octet, it only ever has 2 electrons. And I think that's obvious. It's in the first period, it's only got that inner energy level that can take a maximum of 2 electrons. So if you notice, hydrogen's happy, it's got its 2 electrons. Okay, oxygen's happy, it's got its octet. But if you look at carbon, carbon, remember, is in that second row, that second period of the periodic table. It has to have an octet because it's not the beryllium-boron exception. So what do I do, thinking of level 2 chemistry, what do I do to try and make carbon happy? Okay, Rebecca, I see is typing. You put the double bond. Great. So what you do is remove one of these electrons that are around the oxygen and make them shared between the carbon and oxygen. So basically I've taken that pair, zipped them over there, and now carbon's got 4 pairs or 8 electrons in octet. Okay, so that's the way you work through it. Now I don't want to use up all my time on this, so I'm going to actually skip out of here and show you there are some lovely animations which should be on your OTL sheet on how to, you know, do this sort of online. It just sort of helps you. So for example, we'll just do this particular one. Create the Lewis structure of CF4. So you enter, first of all, remember we said the total number of carbon atom, total number of valence electrons. So we've got 4 for the carbon, and fluorine's group 17. So it's how many electrons, valence electrons, if it's in group 17? Okay, you got the total number. Great. Okay, so you do the 32 in there, you submit. This is correct. Next question. And can you see if you do this? Here it's the same thing. We've decided on the central atom, and you now put in a pair of electrons. One line represents a pair of electrons, so you can draw a line for a bond instead of a 2 dots. And so we have got that sorted. Now we do the next step. So it's the same sort of steps we've done on that PowerPoint, but now you're doing it sort of online as an interactive online. Okay, and let me just finish this one off. So notice how every time I put a pair of electrons on there, that drops and it tells me how many I've got left. Whoops, daisy. Now I've got 0 left. And then you can say, right, and okay, place any remaining electrons. I don't have any remaining electrons, so I can't put anything on there, and it's the next one. Okay. So, you know, you can use that and try that out. Okay, so let me go back to this one again. I want to go over here. Now, won't have time to work through these, you know, together, but I just want to highlight a few things. Ozone can be quite a tricky one because, you know, you think it should all be identical because it's all oxygen, but it actually isn't. So notice that there's a single bond and a double bond when you try that one out. Okay, you have to have a single bond and a double bond because it needs that to get an octet on each one. If you have just a double bond and a double bond, you're not going to be using up all your valence electrons. So always work out your valence electrons before you start, and then when you've drawn your Lewis structure, count the valence electrons afterwards so that you can check if you've made a mistake or not. because usually the mistake in the valence the Lewis structure is because you didn't put the right number of valence electrons down. Okay. For ammonium, it's a cation. Now, for cations and anions, you have to show the positive and the negative charge, and the way you do it is you put square brackets around your Lewis structure, and then you put the charge on the outside. So that's the convention you use. Don't forget that. You're not going to get it right if you leave out the square brackets. There's 3 places in level 3 chemistry where we use square brackets, and this is one of them in Lewis structures for ions. If you think of nitrogen has got 5 valence electrons, each hydrogen has got 4, so I've got 9 valence electrons. What will that positive charge do? Do I add another valence electron and say I've got 10 electrons to play with, or do I subtract an electron and say I've got 8 electrons to play with? So is it 10 or is it 8? Great, you subtract because it's a positive charge. Remember, electrons are negative, so if ammonium has got a positive charge, it means I must have removed an electron from the 9, so I've only got 8 left. And that's why I've got 2 in that one, 4, 6, and 8. All my valence electrons are used up. Xenon, now remember xenon, the noble gases lower down. You can force them to react under high temperature and pressure with oxygen and fluorine because those are the very reactive elements. So notice you can either draw it with single bonds like this, or you can draw it with double bonds. Once you get into the 3rd energy level or higher, and particularly higher, there's a lot of extra orbitals you can use, so you don't have to obey the octet rule, and that's why xenon can have quite a lot of electrons around it. So only those in the 2nd period must have an octet. The others, you could have more. Now here's an example of an acid. So with an acid, notice that the acidic hydrogens are not bonded to the central atom. Okay, so when you count your number of electrons and then you put in your central atom, if you recognize it as an acid, so nitric acid, phosphoric acid, sulfuric acid, if you recognize it as an acid, it will not be bonded directly to your sulfur or your carbon or your nitrogen or whatever it happens to be. It will always be bonded to an oxygen. It's just the OH bond is nice and polarized, so it's easier to remove that hydrogen, and that's what an acid is. It's to remove a hydrogen, a proton donor. Okay, and notice you could draw them like this or like that. Again, if you carried on with chemistry, you'll learn what are better ways or what is not such a good way. But as far as we're concerned, both are acceptable. This one, because oxygen has got an octet, has an octet, has an octet. Sulfur also has an octet. So this one is acceptable. Here, does sulfur have an octet? So yes or no. Does it have 8 electrons around it, or does it have more than 8? It's got more than 8, correct. But sulfur is in the 3rd period. So elements in the 3rd period, particularly like chlorine, sulfur, the ones on towards the right, can access the d orbitals and mix them up. So they don't have to obey the octet rule. At level 2, you learned there has to be an octet. Level 3, you learn that there's actually quite a few exceptions, and it starts getting a little bit more muddy. So that is also an acceptable structure. Okay. Then for the hydrogen phosphate ion, remember we've got 2 negatives, so we have to add on 2 electrons. So when you work out 1 hydrogen, 5 for phosphorus, 4 times 6 for oxygen, plus 2 is the total number of valence electrons. And notice phosphorus is also in group 3. Sorry, not group 3, period 3. So it can access those d orbitals and do a bit of a muddle up, so it doesn't have to obey an octet. Okay, that's as much as I want to do on Lewis structures. Are you all okay? Do you think you could do that? Okay. As I say, they achieved to merit level. Now, these are the ones I used just now. Well, I used this one over here, but here's another one as well. So if you, again, just Google Wananta and Lewis structures, you should come up with both of them in your Google search if you want to do your own things. Okay, right. Now we get on to, once we've got the Lewis structures, or if I just go back a bit, can you see the point of the Lewis structure is it tells you the number of regions of negative charge around that central atom. That's the reason why we draw them, because that will then tell you the shape of the molecule. So we have to count the total number of regions of negative charge. That's what you focus on first. Before you go, I've got bonding pairs or non-bonding pairs or so on of electrons. You always work out the electron geometry. Now, if you think of your electron geometry, and I'm going to just skip over here and go to the next one. With your electron geometry, we've got either, remember electrons are negative, and what do negatives do to each other? They repel. Okay, they repulse each other. So they're going to repel, and they're going to repel each other as much as possible in all 3 directions, not just linear. So if I've got 2 regions of negative charge, then to get as far away as from each other in all directions, they have to be 180 degrees from each other. Okay, so this is for 2 areas of negative charge. For 3 areas of negative charge around the central atom, I'm going to have, it's actually still going to be planar, but they're going to now be 120 degrees from each other. If I try and move one closer to the other, then they're going to just repel again. 4 is the tetrahedral. Now you've learned all of those at level 2. Level 3, you add on 2 more. So the next one is the trigonal bipyramidal, so that's a new one to learn. And then this last one is the octahedral. So that's, you've got 2 more to learn now of those basic shapes and for the electron geometry. So you can work through that, but before I do that, I want to just go on this one. This helps see the shape. So if I click, this is FET, so it's also in your OTL thing, and it's quite nice because you can drag it around. And can you see, this is a region of negative charge as well as there. So if I try and bring this closer to the other one, they repel and they'll just go apart again. If I add another one, you can see it's a trigonal planar. If I add another one, you can see it's the tetrahedral shape. And if I try and make it closer to the other ones, it just simply repels. And I can add one more, and then the last one you have to learn is the octahedral. Now notice with the octahedral, if I look down one axis, then I've got like a square around it. Do you agree? Yep. So in the octahedral, it's totally symmetrical shape in terms of, if I take any one of these, I'm always going to look down an axis and I'm going to have the square shape. If, however, I have the other one, which is the trigonal bipyramidal, notice that I have got 2 distinct axes, the axial plane and then the equatorial plane. So notice if I look down this one all the way through, do you agree that I've got the trigonal planar around it? Okay, so this bond angle is 120, but if I, oops, oh, it can be quite hard to, here's my axis over here, sorry. Nyok. Okay, it's just determined to be a pain. But if I look down the axial plane, so that's 120, but it is actually, there, that's it. Gosh. Okay, can you see that that is 90 degrees? So I can show the bond angles and you can see it's 90 degrees. Now notice, if I move this around, it can be a bit tricky, so I look directly down an atom in the equatorial plane, do I see that same trigonal planar around it, or do I see more? Okay, so Rebecca, you're saying I'm seeing the, so just think of here, if I look directly down here, I'm seeing two atoms in the equatorial plane as well as the two in the axial plane, the one above and below the equatorial plane. Whereas if I'm looking at the down the axial plane, notice I don't actually see the atom right at the other end of the axial plane, I only see the equatorial plane. Now this is important because it's not, it is a totally symmetrical molecule, but it's important once you start getting your lone pairs come in. So if I remove this all, what do I mean by lone pairs? It's when it's not bonded to another atom. So there I've got 4, now the 5th one is a lone pair. Notice where it went into. It went into what, the equatorial plane or the axial plane? Just say A or E. Where do you think this one is? Is this in the axial plane or is it in the equatorial plane? It's in the equatorial plane. The reason being is with a lone pair of electrons, they're only held tightly by one atom, one nucleus, whereas a bonding pair of electrons are held by 2 nuclei, so they're much more limited to where they can go. So a lone pair of electrons can spread out a bit more. So because it spreads out a bit more, it wants room. Now remember the bond angle here is 90 degrees compared to the bond angle, oops, can be a bit tricky. I'm trying to show the 120 degree bond angle, and it's actually not that easy. It's determined to be a, there, can you see the 120 there? If you're in the equatorial plane, you see it as 120 degrees. So play with that and make sure you can carefully see where those lone pairs of electrons are going to go in. Now, in your booklet, sorry, I meant to go, sorry, let me just, I did something stupid here. In your booklet, you've got these shapes that you've got to learn, okay? And you've then also got the ones that have lone pairs with it. So just before we finish, because I think we won't get anywhere near polarity today, but as long as you've got the sort of idea of shapes in your head, because you have to learn these basic things, is to use the Quizlets, okay? So either make flashcards, or one way is to use the Quizlets, and they should also be there, so it's either with flashcards, and you can test yourself like this, okay, either put the one first or the other way you can use the Quizlet is by doing matching games, okay, so you make everything disappear. So for instance, what is this particular one? If you've learnt it, you should know it's bent, a trigonal planar, you hopefully will match it there, and you can race yourself against the clock. So Caleb, I'll check if they're not if they're in OTL, but otherwise, okay, I'll send them, I'll put them, once I've put this video up in OTL News, I'll put the Quizlet links. In fact, I'll put all these things up there so you can find it